Imagine powering up a massive, roaring industrial furnace just to heat a single tiny wire. This exact situation plays out inside modern data centers. The computational density of flagship hardware, like the NVIDIA H100, has vastly outpaced the resource requirements of typical single-process machine learning workloads. Take low-batch inference, or serving a small 256 million parameter language model. These processes require only a fraction of the available memory bandwidth and compute cycles. Yet the traditional paradigm dictates that we assign an entire exclusive device to each process. When you deploy these lightweight tasks on a top-tier accelerator, the majority of the silicon simply sits idle, waiting for work that isn't there. That underutilization drives massive infrastructure bloat. To achieve economic viability at scale, teams must transition away from monolithic scaling and adopt heterogeneous GPU sharing. The new architectural baseline requires packing an array of smaller, distinct models onto the exact same piece of physical silicon. Executing this requires coordination across 3 layers of the stack: the hardware-level architecture, driver-level services, and the cluster-level orchestration layer. If these layers are misaligned, the operational hazards are immediate. Multiple models competing for unpartitioned resources will trigger out-of-memory errors and severe resource contention, ultimately crashing the node. This happens because the default behavior of machine learning frameworks inherently opposes shared resources. By design, they assume they have the entire device to themselves. To solve this, practitioners must stop treating the GPU as an atomic, indivisible unit. We have to look inside the device and understand exactly how its schedules work. At the foundational hardware level, a GPU does not process a workload as a single monolithic task. It breaks the work down and maps it across a massive grid. When an application needs the GPU, it creates a CUDA context. This is a strict software encapsulation of all the hardware resources necessary for the program to manage memory and launch work. The compute engine itself consists of a hierarchy of streaming multiprocessors, or SMs. The driver aliases CUDA streams onto hardware work queues, which then route in-order commands directly to these specific SM blocks. If we submit a lightweight inference task, it might only require enough parallel threads to successfully occupy 10% of those available SM blocks. The remaining 90% of the SM blocks on the grid are completely idle. They are powered on, but processing nothing. Here is the hardware limitation. By default, work originating from different CUDA contexts cannot execute concurrently on the same compute engine. Even if you have the physical capacity to run 9 more models, the isolation of the CUDA context prevents it. Unless you introduce driver-level mechanisms to manipulate or bypass these boundaries, 90% of your hardware investment yields zero return. To reclaim that idle silicon, NVIDIA provides 3 primary driver-level paradigms designed to force distinct processes to share the GPU. The first is time-slicing, or temporal multiplexing. This is a purely software-based approach that interleaves execution contexts over time. This chart from NVIDIA details the scheduling breakdown. Looking at the preemptive scheduling model on the left, we see how time-slicing operates. Processes A, B, and C receive fixed time intervals. They swap in and out, taking turns with full access to the GPU. While this increases user density, it introduces context switching overhead and latency jitter. For production machine learning, time slicing has a critical vulnerability. It provides absolutely no memory isolation between the processes. If one model spikes in its memory demand, it can trigger an out-of-memory crash that takes down every workload sharing the node. To solve the latency and overhead problem, we look to the concurrent scheduling model on the right side of the chart. This is the Multi-Process Service, or MPS, which relies on spatial multiplexing. MPS acts as a control server that allows multiple client processes to share a single unified CUDA context. Because they share a context, the hardware scheduler can dispatch their kernels to different SMs simultaneously, eliminating the context switching penalty. The third option is multi-instance GPU, or MIG. Available on Ampere architectures and newer, MIG is a strict hardware alternative. Unlike software-based time slicing or the shared context of MPS, MIG physically partitions the GPU's VRAM, caches, and compute paths. Each instance operates as a fully isolated separate device. These three driver mechanisms successfully partition the silicon, but they are low-level tools. They lack the cluster awareness required to map distributed Python deployments, like an LLM inference pipeline, down to those specific hardware partitions. This is where the cluster orchestration layer steps in. Frameworks like Ray Core and Ray Serve act as the bridge, mapping Python deployments to the underlying hardware. Ray's specific architectural innovation is its decoupling of physical hardware limits from logical scheduling requirements. Developers can request fractional capacity using floating point demands. For instance, a worker might request exactly 0.25 GPUs. But this logical abstraction creates an administrative illusion. When an actor requesting a quarter of a GPU drops down to the actual execution layer, it can easily saturate 100% of the physical hardware. Ray Scheduler does not enforce hardware-level limits on compute. It enforces basic isolation solely by setting the CUDA physical devices environment variable, assigning the exact same physical index, like device 0, to multiple fractional workers. Machine learning frameworks like PyTorch and vLLM respect this variable and initialize on the specified device, but they remain completely oblivious to the fractional intent of the orchestrator. If two fractional workers NOP on device 0, and each engine attempts to claim the entire VRAM pool to maximize its key value cache, the node experiences an immediate out-of-memory failure cascade. A fractional resource request in Ray is useless on its own. It requires explicit alignment to the framework-level memory management and the Kubernetes device plugins to enforce actual physical boundaries. Exposing these fractional slices to containerized workers safely requires integrating the Kubernetes stack. The NVIDIA GPU Operator manages the full lifecycle of the hardware through a continuous reconciliation loop. When time slicing or MPS is enabled, the device plugin registers the replicas and advertises them to the kubelet. To the Kubernetes API, these appear as fully available logical nvidia.com/GPU resources. The final required step falls to the practitioner. You must manually tune the framework engines. For example, setting vLLM's GPU memory utilization flag to explicitly match the fraction specified in Ray's placement group configuration. True infrastructure stability is achieved only when the Python orchestration API, the Kubernetes resource limits, and the low-level framework memory managers are in perfect synchronization. When you successfully orchestrate multiple distinct models onto a shared piece of silicon, the latency payoff for complex pipelines is massive. Ray Serve optimizes pipelines by placing child replicas on the same node as their parents. When sharing a GPU, data moves directly through Ray's shared memory object store. This zero-copy transfer means the payload never leaves the VRAM, bypassing the CPU bottleneck entirely. For infrastructure architects, choosing how to partition that GPU requires a strict evaluation of the workload. Time slicing is ideal for highly heterogeneous, bursty workloads where you need to maximize user density and can tolerate a lack of strict isolation. MPS offers spatial multiplexing for concurrent, high-throughput inference in trusted environments where memory usage is predictable. If you need absolute multi-tenant hardware isolation, you deploy MIG. Raw compute density has outpaced monolithic scaling. Mastering the interplay between Ray's logical fractionalization and physical hardware sharing unlocks the true economic potential of modern AI accelerators.